Welcome everyone. Today we are going to start the session 6 of operating system and Linux. I'm Manibhushan D'Souza, and today's class we are going to see process scheduling. So let's look at what is the meaning of process scheduling and why process scheduling is required in the operating system. Before we venture into process scheduling, let's look at what is the meaning of saying scheduling. So we know that our timetable will schedule our classes. So we know which classes is going to start first, which is going to be the next class, and so on. So every day of the week, what classes will be there, and when there will be a lunch break, and so on and so forth. This is scheduling. So scheduling will help us in controlling the classes that we attend in our college. In the same way, scheduling is required even for the operating system. So, what is process scheduling? So, process scheduling is nothing but it's a set of policies, so set of guidelines, as well as set of mechanism that controls the order in which processes need to be completed. So we know that in a operating system at any instance of time there will be number of processes. So some of the processes may take longer time, some of the processes may take shorter time, and some of them may require a lot of resources, and so on and so forth. So which among them has to be selected first, which one has to be selected next, and which will come after that? This is nothing but scheduling. So we follow a policy or certain guidelines that help in choosing the processes for their execution. In all the operating system, there is a special program called as scheduler, which is responsible for scheduling all the processes. In other words, the scheduler is responsible for selecting the next process that will go for the execution. In almost all schedulers, the objective of the scheduling is to increase the utilization of the CPU. We know that CPU is one of the main and one of the important component of the computer system, and if the CPU is busy, then a lot of works can be done. If the CPU is idle, then no work can be done. So we need to see to it that CPU is utilized to its fullest extent so that more number of works can be completed in a given time interval. Now, whenever we start our process, for example, if you go to the desktop and double click on the Microsoft Word icon, or maybe some other icon which is there, the shortcuts which are there, then a process is going to be selected. Now, if you look at this as the RAM of your system, when you double click or when you activate any of the process, maybe it is a Word document, maybe it is an Excel document, maybe it is the game that you want to start. So when the process, which is generally a program that resides on the disk, so when this process is loaded from the disk to the RAM, it stays in a queue that is called as job queue. So there is a queue which contains the process. So the first process to start will be the first in the queue, second will occupy the second, and so on and so forth. So when the process comes enter into the system, it is put in the job queue. So job queue will contain all the processes which are there on the system, so which are there to be executed within the system. Now, Again, let's look at the RAM. So this job queue will contain all the processes. That is what I have told you. But every process requires some or other resources. And if the processes has all the resource, what I mean by saying that all the resources, your program may require some files to be opened. For example, if you want to play music, then you have to supply a MP3 or maybe some other audio file to your program. Otherwise, it will not run. Again, if you want to play a movie, then that movie has to be first loaded. Now remember, there is this media player or any other player that you may think of using. That's a program, but that program requires a movie to be loaded, then only it is able to show the content to you. So when it gets that movie, when everything is there, and it requires in order to produce the sound, it requires the speaker. So that is also a requirement. So you require a speaker in order to play the output. Okay, so when all these things are available, then the program can execute. But the problem is, program can't execute because execution is done by CPU. So that is where, so in other words, the instructions are executed or instructions are carried out by the CPU or the microprocessor. Unless the microprocessor takes up the instruction, nothing is going to happen. Even if you load the movie, even if the audio system is there, nothing is going to come out because microprocessor is not doing any work. So when these processors have everything that is they require except the CPU, remember they don't have the CPU, then they are said to be ready and they are kept in the ready queue. So processes which are residing in the memory that are ready and waiting to be executed. What do we mean by saying ready and waiting for execution? Is they have everything. The movie file is there or the audio file is there. The connection to the speaker is if you take the speaker as a resource. So audio system is there with it. That resource is also there, but the CPU is not there. So it is just waiting for the CPU so that it can start executing. Such a processes are kept in a different queue, and what is that queue is called as? That queue is called as ready queue. So what is there in the ready queue? Ready queue will contain all the processes. Remember, there is not you don't expect that there is only one process which are waiting. There may be many processes which are waiting for the CPU. They have every resource that they require to execute, but the CPU is not there. CPU is not executing it. So all these processes which have everything with them, but they don't have the CPU, they are kept in the ready queue. Okay, so ready queue is generally stored in the form of a linked list. So even though I showed you a queue, which you may get it from your ordinary idea of creating an array and storing it in an array, that is what you might have studied in your data structures, wherein you created a stack and queue or a circular queue or other thing with an array. But here the queue is not in the form of a array, but it is in the form of a linked list. So all the processes will be in the form of a linked list which are kept one after the other. So if I take this one as process 1, this one as process 2, and maybe this one as process 3, if I take all these three, they are connected to one another. So one is connected to the other, second one is connected to the other, and there is going to be a header that will say what is the starting. So what is the starting point? That is the starting queue is this, and what is you know very well what is the end, which one is going to be the end of the queue. Now you may say that why sir end is required. I am talking about the queue, and you know very well in the queue, if at all you want to place one more item in the queue, then it will come at the end of the queue, not at the beginning of the queue. So I need the last queue, which will point to the definitely to the other queue. So there will be starting pointer and there will be ending pointer, and we know very well that for a process to be there in the memory, to be recognized by the operating system, it requires process control block. All the information regarding the process will be kept in the process control block, which contains a program counter, which contains all the registry and so on and so forth. I have discussed about it. If you really don't get what I'm talking about, please watch my previous videos, and I have the details on that process control blocks. Okay, so every process control block will contain a pointer to the next block. Okay, and there will be a header that contains a pointer to the first as well as the last block. Now we know that we have a process. Let's assume that you have a process and it is executing. So this is let's assume that this is the CPU, and this is your favorite process P1. Let me say this is the process P1 and it is executing its instruction, and the CPU is doing all the executing all the instructions. Suddenly there is a input output request. So you know very well, whenever there is an input output request, CPU will not wait for the input or output. Why? Because all the devices, whichever device you think of, all the input output devices are very extremely slow as compared to the speed of the CPU. CPU works at extremely or terribly faster, whereas input output any device for that matter cannot compete with the speed of the CPU. So what the CPU will do, whenever there is a input output request by any process, that process is interrupted. It cannot proceed. For example, in your C program, I hope you can remember this, you have written scanf and maybe percentage %d, and you might have used this ampersand symbol. So what is this ampersand n something you have this kind of program you have written. So assume that this is ampersand. I don't get that ampersand here. So ampersand n, suppose, then what will happen? The program will stop for the n value to be entered. So program will wait. When you say program will wait, your CPU is also waiting. So waiting for an input. Okay. Now, the input may come from your keyboard. In this particular case, the input will come from your keyboard. In the same way, you might be playing a movie, and or maybe you are playing a audio, and one song is over, next song will come from your playlist. So until the next song is loaded from your playlist, or maybe in the movie, if you are continuously watching a movie, it is possible maybe you're watching the songs, the video songs, or maybe serial or something. So one song is over, the next song has to be loaded. Until that next song is loaded, everything is put into halt because it takes some time. So what happens is, in that case, your processes will go to the hard disk. In this case, if the song has to be loaded, you can't type that song, so it has to be loaded from the disk. So your processor or the CPU sends a request to some the other device, and it will ask the device, okay, give me that thing, and then I will proceed. Maybe remember, the CPU will not wait for such a thing. CPU will just make the request and then say, okay, when it comes, you tell me, I will proceed with something else. So CPU is not lazy like us. When something gets stuck, it simply switches to the other. Okay, this is how the operating system really works. Now, if you take a hard disk for that matter, so if you just take a disk for that matter, so you are playing song, no doubt, you want to play song and you are typing your assignment or you're doing some project and your internet explorer is downloading something and maybe your antivirus is checking for the virus. All of them, where do they do their work? They require the data from the disk. So they are storing, you're downloading and storing it in the disk. Your audio files are being loaded from the disk. Your antivirus is searching. You are trying to save your project into the disk. So for this disk, so many requests have arrived. So what it will do, it will maintain a queue for of all the processes which have made the request. Otherwise it will lose control of who has requested first, who has requested next, and so on. So again there will be a problem. So what the disk will do in this case, the disk will also say that I have a queue and whoever came first will get the first, the next one will be in the next queue, and that is called as the device queue. Remember, every device has its own queue. So your disk has a queue, your keyboard may have the thing, your monitor may also have. You can think about that. Generalizing, I'm just generalizing, not that it is required. So mostly it is the disk. If you have two hard disks or maybe a tape drive or a CD-ROM or this kind of devices, they have the queue and the process will be kept in that queue. So the device will keep that process, saying that okay, it has made a request. So let's look at how the things are working. Now this is regarding the your device queue. So if you look at there is a device called as a magnetic tape and nobody has made a request. That's a good thing. There is one other magnetic tape and fortunately nobody has made a request, but there is a disk and there is this first process, process 3. It has made a request. Remember, the queue is I've already told you, it is not the array, it's a linked list. Then process 14 is there, then process 6 is there, and it is waiting. Again you have finally this has been grounded. Hope you know, you've studied about the data structure, so you know what is the meaning of saying grounding. So you have the one other terminal is there. So there is one process which is waiting and it is grounded, nobody else is there. Now this is your ready queue. So this ready queue will contain again same thing, a header that points to the first, then it points, the first one will point to the next one and so on, and last will be grounded, as well as the tail will or the end or tail, whatever you call it as, will point to the last one. Okay. Now in order for us to look at how the queuing really works, so now you know, a picture is worth of 1,000 words. So if I just tell you that no, it is that the CPU is there, that queue is there, that process is accessing, you will get wild imagination. Some of you will get some strange imagination, others will get some other, maybe some of you may get the right idea. But if I want everybody to be on the same page, what I have to do is I have to draw a diagram. That's what I have done. I have drawn a diagram and shown you that okay, this is how it really works. Okay, so a common way of representing this queuing or scheduling is using a queuing diagram. So in this queuing diagram, the queue is represented in the form of a rectangle. Okay, so all this queue, maybe it is a ready queue or this input output queue, all these queues are represented in the form of a rectangle. You must remember that. Okay, there are two types of queues that generally being used. One is the ready queue and the other one is the device queue, which I have already shown you. All the resources are shown in this circle. So this is one resource. CPU is one of the main resource. Now if you say that okay sir, why this CPU is one of the important and the main resource. Without CPU nothing is going to happen. This is one input output resource that you may have. So how does the thing will work? Okay, there will be a process in the ready queue and this process will be given the CPU and they will start executing. As they start executing, if they make a input output request, then they will be kept in the input output queue of the specific device. And once the input output for what they are waiting for, suppose they are waiting for a keyboard input. Once the keyboard input arrives, they will come back again to the ready queue, and this process will continue. And we know that what is a time sharing machine. So what is time sharing machine? So you have this process P which is working, which is getting executed by the CPU, and let's say a time of 1 second is given for this particular, a quanta of 1 second is given. So when after 1 second, what will happen? CPU will, once the time has expired, will send it back to the ready queue, and CPU will start working with some other process whichever is there in the front of the queue. There is the other thing that can happen. So you have a process which is working, which is currently executing, and this process may start some other process. So it is possible. Okay. For example, I am just giving you an example. You downloaded something from the internet, and it says download completed, and you double click on this. So when you double click, what will happen? You are there in the Chrome or Firefox or other thing. You are in one process. That process will start something else. So if it is a PDF document that you have downloaded, when you double click on it, maybe Acrobat or any other PDF viewer is there, that's going to open. So one process starts the other. So this is called as a parent process, and the other one is definitely called as the child process. So a process may, we don't say it creates, we say it forks a child process. Okay, and the child process starts executing. Now during this time, the two things can happen. The parent which started the child process may wait for the child to complete. That is one possibility. So parent waits for the child to complete, or parent will start the child process and parent will go on its own. Two possibilities are there. Okay, so if suppose if the parent has started, and if the parent is waiting for the child to complete, then parent will go and stay in the ready queue. Now going to the last option. So you have a process here, and the CPU is executing, and suddenly an interrupt occurs. So remember, whenever there is an interrupt, your program will be terminated. So it is interrupted, not terminated. Your program is interrupted, it is suspended, and the whatever interrupt has occurred, for example, if there is an error, not in your program, maybe in the system error is there, or maybe some higher priority work has to be scheduled. In that case, it is interrupted, and your program will be suspended, and it will be being kept in the ready queue. So it goes here interrupted, and then it goes in the ready queue. So this is how the things will work. Again, I've already told you, circle represents the resources and the arrows will represent the flow. So in this case, arrow will show you how the program will work. Now very important thing about this one, I've already talked about what is circle, what is arrow. Now it may so happen that you have a process which is getting executed, and finally at one particular time it will complete. When it completes, it comes out of the queue. There it won't go to the queue because its work is completed. Or it will go back to the queue if something is pending and it is not completed, then you go back. If you completed, then there is no point in it. So you know very well. So those who were there with you in the SSLC, you have completed your SSLC, you are not going back to the supplementary exam. For those who have not completed the SSLC, they will have to go back to the supplementary exam and write the supplementary exam. So if the work is not completed, you go back to the ready queue. If the work is completed, it is all over. You are not going back to the ready queue. As simple as that. So let's look at the queuing diagram. Now we have already seen that thing. Whenever process is initially when it is created, it is kept in the ready queue, and it will wait until the CPU selects. So there may be many others in the queue. It will wait until the CPU selects it and then starts executing it. Okay, once the process is been assigned to the CPU, many things can happen. I have already told you. If there is an input output request, then it will be kept in the input output. So if there is a input output request, your process will be kept in the input output queue. If it creates a new sub process, it will wait for its termination, or it may be forcefully removed if there is an interrupt. So these are all the things which are there. So we have already seen about that. Okay, now we know very well this particular cycle that we see here, putting it into a queue and then going back and coming back to the queue, and again putting it and going back to the queue, and again executing, then going back to this will continue until at one particular point it will simply exit out when the uh, program when everything has been completed, when the processing or when the instructions are being executed. Once the instructions are executed, the process is removed out of the queue. The program control block, which was the process control block, which was given to, which was allotted to it, will be deallocated and it will be given to some other processes. Okay. Now, when we talk about the schedulers, so there are different types of schedulers. The operating system must select an appropriate process so that the entire thing happens in an efficient manner. Okay. Now this selection of the process is carried out by the schedulers. We are familiar with that. There are three types of schedulers are there. One is short-term scheduler, other one is long-term scheduler, and the third one is the medium-term scheduler. Okay. What is short-term scheduler? Short-term scheduler, it is also called as a CPU scheduler. Okay. Now we know that some process will be there in the ready queue, and CPU will select them, and they start working, and if there is an interrupt they will come back to the ready queue. So there, at an instance of time, there will be many processes which are waiting in this ready queue, and which one has to be taken from the ready queue? Is it the first come first serve, or is it this one, is it this one, is it this one? Which one has to be selected from the ready queue and to be given to the CPU? That is decided by the short term scheduler. So work of the short term scheduler is to go and look into the ready queue and select one of the appropriate process and give it to the CPU. Okay, why we call it as a short-term scheduler? Because it is called again and again and again. Remember, at any instance of time, a process is given to the CPU. It will not be there for 1 hour. It will be there for some quanta of time. You know about the time sharing machine. So it will be there for some amount of time, maybe 1 second maximum. So it will be there for 1 second. After 1 second, it will be forcefully pulled out because its time slice is over, and it will be kept back in the ready queue again. Something else will be scheduled. Okay, if this process is running and if there is an input output request before the quanta time, then it will be pulled out. So that means at any instance of time, a lot of processes are scheduled. Some of them get suspended, some of them interrupted, some of them get terminated because of the completion, and so on and so forth. So at any instance of time, lot of processes has to be given to the CPUs, and this particular short-term process is called every now and then, because every time its work is to pick the best from the queue and give it to the scheduler. That's why we call it as short term. So because it is called frequently. Okay. In general, it is called for every 10 milliseconds it is called. So such a short term. So it you won't allow it to sleep. Every now and then you go and say, okay, schedule the next one, schedule the next one, schedule the next one, and so on. So it is called very frequently. Short term, within a short term, that scheduler is called again and again to perform this work. Because it is called every now and then, it should be very efficient. Okay, it should quickly find the next process and give it to the CPU. Remember, scheduler is also a process. Nothing is magic here. Schedulers, there is some algorithm. You have seen the algorithm to find using binary search and so on and so forth. Somehow you find the item very quickly. So similarly, scheduler has some way, some algorithm to search and find for something, and it has to be very efficient. Very quickly it has to do it. For example, if you are if the time limit is 10 milliseconds for a given process, quanta time. So what is the meaning of it is, you know very well, if you have a queue here, and if you have a CPU here, if one process is given, that process can execute up to quanta time. So quanta means every process is given a small time slice within which it has to execute. If it has not completed, it will be pulled out, and then something else will be rescheduled. So time sharing idea, you are very familiar with it. So suppose say time quanta is 10 millisecond, and if the process takes 1 milliseconds to decide on the process. So if your short term scheduler takes 1 millisecond to decide which among them is the best one. So what is the amount of time it is taking? It is taking 1 by 1 over 10 plus 1. 10 is your quanta. So it is going to be 9% of time is wasted by the of the CPU time is wasted, because it is taken up by your scheduler, and so every process will get 95%. So 91%, 9% of the CPU time is wasted by the scheduler itself. So remember, so such a it should do it very quickly. So otherwise, if it is taking 5 milliseconds, it's going to be terribly long time. Most of the CPU time is wasted by the scheduler itself. So now let's look at the other type of scheduler, and the other type of scheduler is called as a long-term scheduler. Why do you think it is called as long-term scheduler? Because it is called after very long time. It is not very frequently called. It is called once, and then it can relax, take a cup of coffee, or maybe watch a movie, and then after some time the CPU will call again. Okay, schedule now. So that's why it is called as a long-term scheduler. It's also called as a job scheduler. So what is the work of the job scheduler? Remember, at any instance of time, there will be many processes which are waiting in the CPU, waiting for waiting to be brought to the memory. Okay. So these are called as pools, process pools. So there will be many processes. Everybody say, hey, I want to get executed, I want to get executed, I want to get executed. Some of them are fortunate enough to be reach to that particular RAM and then get executed. So what is the work of the long-term scheduler is to select one job from the waiting job and then put it into the memory. That's the only work it has. Okay. So what it is doing is, its work is to start that process, in simple word. So you just start that process. So its work is to go and say, okay, you come, you start executing it. During the execution, it may go for input output request and so on. In that case, it will go back to ready queue and it will keep on circulating. That part is taken care by the short term scheduler. So once it enters into the ready queue, it's a short term scheduler that does it. But long term scheduler's work is to load that job into the memory. That's the only thing it does. Remember, every now and then you don't load the things. So when you start your computer, you start your Internet Explorer, you start playing the songs, and maybe your antivirus is running behind the scene, and that's all. Every now and then you don't simply go on clicking on the shortcuts and start opening all the applications. So in your mobile also, you don't tap on all the icons there and start all the application at a time. Maybe you start 4 or 5. So 4 or 5 out of 4, one has to be selected. or 2 has to be selected. So its work is that's how many times do you start a new process as a single user. Maybe in the multi-user many things can come, but as a single user, you know very well, starting process is a very rare process, maybe rare phenomena. That's why this scheduler is called after very long time. So what's the work of this particular scheduler is it helps in the controlling the degree of multi-programming. So how many programs should be there in the memory at any given instant of time, that is decided by the long-term scheduler. So how many programs are there in the memory will decide the extent of multi-programming. What's the meaning of saying multi-programming? Putting more than one program in the memory and then executing them concurrently. Okay, so in order for to have a good degree of multi-programming, generally what is done is what this particular process will do is once the queue is full, what it does is initially it is called. So it will keep on adding one, and once everything is full, it will simply keep quiet. When one of them terminates in the sense when one of them completes its work, then it will start deciding on which is the next one that has to come. So on an average, okay, rate of process creation is equal to the rate of departure. So when one goes out, the other has to come into the picture. So it will not simply keep on loading it. So it will wait. Okay, if memory is full, no more space is allowed, then it will simply wait. Okay, one of them terminates, it starts the other one and then starts doing it. Okay, so the long-term schedulers are called only when one of the process completes or leaves the system. Okay, so there will be a long pause or longer interval or longer duration before which this particular scheduler is called. Now, very important thing about the scheduler is when we talk about any program or any process for that matter, there are two types of processes are there. One is called as input output bound process. The other one is called as a CPU bound process. So CPU bound process means these process takes lot of CPU cycles to complete their work. So they are doing lot of calculation, but they don't require lot of inputs. Generally, the scientific programs are there, which have some data. Then lot of calculations are done on the same data for a lot of heavy duty calculation like sine, cos, tan, integration, limit, and so on and so forth. So the same type of data, but a lot of computation. So the CPU time is utilized heavily here. Whereas if you look at this commerce related data, so in commerce, you have debits and credit. Either you add, either you subtract. That's all. Adding a subtraction is a child's play for a microprocessor. It's nothing. Adding and subtraction is nothing for a microprocessor. So CPU time is very less, but a lot of data will be there. So if you look at the accounts, lot of inputs are required. Every data is required, so it has to read lots and lots of data, and it has to write back lots and lots of data. But what is the calculation it is doing? Nothing, simply adding and subtracting. So CPU is least used, but input output is used heavily here because lot of data has to be read. So there are two types of processes are there, and this long-term scheduler must decide which type of processes are loaded. Suppose if it loads only CPU bound processes are loaded, then what will happen is CPU is overcrowded lot of things. So that means to say your ready queue is full because everybody is waiting for a CPU, and once anybody enters a CPU, they will take the full quanta time because they don't want any extra data. They will take the full time. So CPU is busy. What about the input output device queues? Device queues are empty because nobody is making any request. Nobody wants the data. So nobody is requesting anything from the input output device. So they are simply ideally they are sleeping. Okay, so this is not a good scheduling. Why? Because you are using only CPU. If you want an efficient system, that means you have to not only use CPU, you have to also make the best use of even the peripheral devices, that's the input output devices. Everything must be put into action, not just one of them is tortured by giving extra work. So that's not a great idea. What about the extreme side? So if you have a input output bound process, then your input output devices are very busy. So input output queues are full, always full, lot of requests for input. What about CPU? CPU is simply sleeping. It says nobody is giving any work. They are simply getting data. They are simply transferring data. That's the only thing they are doing. I have nothing to be done. So this is again bad scheduling. So it must make a balance between the CPU bound as well as the input output bound system or the process, so that the scheduling is proper. Okay. In general, when we talk about the time sharing machines, they generally don't have the long-term scheduler. The reason for that is there will be a limit on the time sharing system. So how many processes will come into the memory will be decided by the capacity of the memory. If it is not beyond that capacity, it cannot load it. Also, how many people are going to be using the system will decide on how many terminals are there connected to the particular system. At the same time, if many people are connected to a time sharing machine, so like a Unix system or any other, and you connect to the internet, and nothing is coming out. So what you will do, you will again refresh it, and then you will just leave out, forget, internet is slow, I will check my mails, or I will use it. Now nowadays such a thing doesn't happen, but you might have experienced maybe during rainy season, or maybe during thunder and lightning, your internet is slow, and you feel that okay, forget, I will do my work later. So what happens is, in the time sharing machines, when the user is typing their command and no response comes, so what you will do, you will simply log out and go. You will quit the system and will do something else, so that automatically the load is balanced. So there is no scheduler as such is required. In generally, the schedules are not required. Now we have two extremes here. One is the short-term scheduler, which is called every now and then. One is a long-term scheduler, which is called once in a while. In between, we have something called as a medium-term scheduler. So what is the work of this medium term scheduler is, sometime if the processes are there in the queue, in order to maintain the degree of multi-programming, what the medium-term scheduler will do is, it will remove some of the processes and it will transfer them to the disk. Okay, and when at appropriate time, it will call them back to the process. Why it is doing so, you may ask, okay, why this kind of work it is doing, sir? This is done because the RAM is very small, and you cannot put a lot of things in the RAM as such. Okay, even though you have a CPU and so on and so forth, you need a RAM. So if the RAM is full, no process can enter. Whatever queue you are talking about, ready queue or any other queue, if the RAM is full, nothing is going to happen. So the RAM will decide the extent of multi-programming. Now suppose if one of the process is simply waiting in the ready queue, there is no point in doing something. In that case, what it can be done is, it can be pulled out of the memory and something else can be brought into this place. And that is what is done by the medium term scheduler. Remember, that is not done very often. Again, that is not done very rarely. It is done somewhere in the middle, not very rare, not very often, in between. That's why it is called as a medium term scheduler. So that is why. Now what happens is, you can increase the degree of multi-programming by clearing some of the process and pulling them out of the memory. You can bring in a new process, and you can increase the number of programs that are running concurrently at a given instant of time. That is what is called as a multi-programming. Now if I told you that you can pull this process out of the RAM. If you pull this out of the RAM, where it will go? it will go to the disk. So you take the PCB, you know what is PCB, process control block. So you take that and you transfer it to the disk, and at the appropriate time you pull it back. It's as simple as that. So in other words, you take the process, state of the process, entire process, take it, put it onto the disk. Disk, you know very well what is the connection between, or what is the relationship between the disk and the RAM. RAM is very very small, disk is very very large. You have 4 GB of RAM, you have 1 terabytes of the 1024 GB of disk, which is very vast. So at any time you can transfer it there. So there is no problem as such. So this is done there. Okay, this idea of taking one process and putting it onto the disk, that is called as swapping. So you swap the process from the RAM to the disk, and at the appropriate time you swap it back. So swapping, taking it from the RAM and putting it into the, so taking your process from the RAM and putting it into a disk, this is called as swap out. So that's called as swapping it out of the RAM, and again definitely bringing it in is called as swapping in. So you can swap out a process, keep it in the RAM, and at appropriate time you can always bring it back. So this is a idea is called as swap out and swap in. Okay, this can help in also improving the process mixing. That means if you find that only input output bound processes are there, only input output processes are there, some of them can be swapped out and CPU bound processes can be brought into it. Or if you find only CPU bound processes are there, some of them can be swapped out and input output process can be brought in. The next thing that we need to know is the context switching. Now I told you that you have this ready queue. In this a lot of processes are waiting and so on, and you have a CPU. It takes one of the process and executes it. After some time, when the quanta is over, it is pulled out and something else is scheduled. That means one process was executing, it has to be removed and something else has to come in its place. This is called as switching. Switching from one process to the other process. In other words, CPU was doing some work with respect to one of the process, let's say process P1, and P1 has some its own variables, its own values, its own all those things. That is called as a context in which a CPU was working. For example, you were sorting 10 numbers in the process P1, and in the process P2 you are doing a linear search, some other program. So in the first one it was doing this bubble sort for I is equal to 1 to n minus 1 or j n minus j minus 1 and so on and so forth. It was doing that one. Suddenly this has to be stopped and something else has to come in between. So this is called as switching from one context to the other context. So what is context switching? Context switching is nothing but switching the CPU to another process and saving the state. Remember, switching is not simply wiping out, it is not clearing everything. If you clear everything, all the calculation it has done is gone. Save the state of the process, then get the context of the other and start working. Okay, so this is called as context switching. Now how does the context switching works? Let's give a simple example. Let's say you have two process P0 and process P1. So let's look at how it really works. So the process P0, you have this process P0. So you have this process P0, it was executing. Now this is the time it was executing. Suddenly the CPU said that no, I want to switch to the process P1. So what it will do? First it will save the state of the process P0. This process P0 state is saved. Then this is one process, remember, and the process P2 is brought. The state of the process P2 is brought. CPU will start executing, and if there is an interrupt, process P1, so if it is a P0 and P1, so I will take P0 and P1. So first P0 is saved, P1 is loaded, P1 is executing. Once something happens, P1 state is saved and something else is loaded and it continues. So this is how it really works. So you save the state of one of the process, load the other state, execute it. Again, if you want to switch, save the state of this one, load the state of the other. Okay. Now we know that very well when I say save the state, what is the meaning of saying save the state? Save the PCB, process control block, because process control block contains all the details. Details about the CPU registers, the state of the process, its memory, and so on. So for that information will be there. Okay. So during the context switching, what happens? The state of the process is saved. So old process is saved, and the state of the new process is loaded. Okay. Now remember, this is again an overhead, because the CPU has to save everything, and something else has to be loaded, during which other work is being done. Okay. So how much time does the system spends in doing the context switch? It really depends on the hardware. First of all, it depends on the hardware. There are some machines, they have a built-in hardware for support for swapping from one doing this context switching from one process to the other. It also depends on how many registers are being used up, because all the data has to be stored. So if lot of data is there, it takes a longer time. If it is less data is there, less time. Typically the range is from 1 to 100 microsecond, a minute, 1000 microsecond, that is 1 millisecond time it will take. So that's all in this class. Thank you for your interest. For more such information, please read the Galvin book. I have referred all the diagrams and all the details from this particular book. In case if you want to learn more about it, please refer this particular book. Thank you.